we're going to examine data that I have acquired here from NASA in regard to ice coverage that we see in the Arctic Sea each year in the month of September. The reason why September is chosen is because that's actually the month each year where the Arctic Sea is covered the least in ice, since in June, July, and August, those are summer months in the northern hemisphere, so the ice has had a lot of opportunity to melt, and even in September when it's still relatively warm outside. So if you take a look through the table here, you'll see that the years span between 1979 through 2021, and then we also have that the ice extent is measured in area in terms of square kilometers, and those numbers are actually in millions of square kilometers. So one thing we might wonder about this data is whether or not there is a correlation that exists between the year and the ice coverage. And so if you kind of take some time to look through the table, you might notice some definite trends and tendencies, and a great definitive way for us to kind of take a look at that is get a picture of this or make a graphical representation of this data. And so since both variables are quantitative, then we can definitely use a scatter plot to be able to plot each of these ordered pairs right here. So in doing so, I did this in Desmos, and so you can see right there that that's what the scatter plot of the data looks like. Do recognize that here along the x-axis there, I've made it be the number of years since 1979, so the x-axis numbers are not actually the years themselves, so it doesn't start at 1979. It's actually that year zero is actually going to be 1979, etc. from there. So it definitely looks like there's a correlation to answer the question, right? And so is there a correlation? Yes, right, to answer that first question. And specifically, what sort of a type? It definitely looks like most of the points kind of fit towards a line, right? So if we were to try to find a line of best fit, you can see that most of the points are pretty close. And so we would be able to classify this, of course, as a linear association, but because the line has a negative slope, or that best fit line does, it definitely has a negative linear tendency that we can classify it as. To be able to interpret this correlation in context of the data, we really want to be able to interpret what that meaning of the negative linear association is in context. So anytime you have a negative linear association, then as x increases, y is decreasing. So in this regard, then we can say that as years increase, because that's your x variable, then the y variable, which is area, then the area of ice cover tends to decrease. And that's an overall trend, right? Does it follow it from one year right to the next? Not always, right? But over time here, right, over these 40-some years, we definitely see that tendency over time there. So one thing that we see a lot with data is, let me draw that line here again. So if we had a scatter plot that had even more points, so let's say we had more of these points out here, now you can see that we would probably call that line kind of a weaker fit, because now I introduce more dots that are further away from the line. Whereas before, so let me erase all these random black dots that I just made right here, most of the points are pretty close to the line, right? It's a pretty decent fit. And it turns out that there is a way for us to measure how good of a fit a line is to a set of points. And so the way we can measure that is by using something that we call a correlation coefficient. So the correlation coefficient is represented with the letter R, the lowercase letter r. So there is a formula to be able to calculate that. We're not going to worry about the calculation of this. We'll just allow technology to do this for us. So there's a couple of things that a correlation coefficient will tell us. Now, ultimately, one thing that you should understand is that when we come up with a value for r is always going to be some number strictly between -1 and 1. So it won't go anywhere outside of that particular range. So what R will tell you is it will tell you how strong a correlation is. So by strong, we mean how well of a fit is your line to your scatter plot, right? So are those points really, really close to the line, or is it pretty weak, so you got a lot of points further away? So it'll tell you about the strength of the correlation. And then it will also tell you about the direction of the correlation, meaning whether it's a positive correlation or a negative correlation. So it's actually really convenient because anytime R is between 0 and 1, that actually tells you that the data is more positively correlated. So when R is a positive number, you've got like a positive correlation tendency going on. Whereas on the other side here, whenever R is a number between -1 and 0, you're always dealing with a negative correlation. So it turns out that the closer and closer you get to 1, or the closer and closer you get to -1, the stronger the fit is. So if you're kind of in the middle-ish, like at -0.5 or 0.5, it's kind of like a moderate fit. And then anytime you're like pretty close to 0, so if you're like -0.2 or you're like positive 0.09, you're pretty close to 0, that's going to be a pretty weak fit. So you're going to have a lot of points very far away. So just in terms of examples of what you're going to see here in terms of scatter plots and then corresponding correlation coefficients. So in the very first scatter plot right here, you can see that the points are actually perfectly in a line. And the R value that corresponds to that is a 1, right? So like I said, anytime the R value is close to 1 or close to -1, that indicates a very strong fit, like the points are going to be very close to fitting to a line. And it turns out that R can actually only equal 1 when the points are perfectly in a line. Okay, and so that's exactly what's happening right here. Also, the fact that 1 is positive relates to the fact that this is a positive correlation. So basically there's a positive kind of slope, right? So these other two on the top right here also have like positive correlations because they have positive slope tendencies, and that's reflected in the R values because they're positive. And you can see kind of then the 0.81 is still pretty strong, and then it starts to get a little bit weaker with that 0.451. And then just down below that, you can see an example where, again, these points are all perfectly in a line, but it's got a negative slope, so that's why you're seeing the R value there of -1, and then a very pretty strong negative correlation there. And then that last example doesn't really show too much of a linear correlation, like it's pretty scattered overall, and so that's why you can see, oh, hey, R is, very close to 0, so you've got almost no correlation existing right there. And then that spectrum right there just kind of shows you what scatter plots might look like with corresponding correlation coefficients. So here we're asked to sketch a scatter plot that matches each description. So for the first one right here, sketch a scatter plot that would have an R value or a correlation coefficient of -0.86. So this right here is pretty close to -1, so it should be a pretty strong fit, like most of the points should be fit pretty close to a line, but then also it's going to have a negative correlation because it's negative, right? So if I just, draw something like this, that's going to be like a line sort of pattern that's negative, and if you were to draw a line of best fit, most of the dots would be pretty close. So that would be kind of a pretty decent accurate sketch. The next one over is -0.08, so it tends to kind of have a negative slope, but 0.08 is pretty close to 0, so it's going to be pretty hard to tell. Like, the points are just going to be kind of scattered all over the place, have a slight negative tendency, but it's just going to be pretty random, almost not correlated at all. The third one right there says to do a moderate positive correlation, linear correlation. So positive, of course, means have a positive slope, and moderate means it's a pretty decent fit. It's not super close, but it's also not super far away. So if you had like, something like this, maybe that might be a little bit more moderate, where it's a little bit more spread out, but definitely, more definitely still a line pattern. And then the last one right there is to do R equals 1, and that means, of course, that the points have to be perfectly on a line. So if you have like those dots right there, they all lie perfectly together on a line, so it's going to have a correlation coefficient of 1. So for our data that we have in regard to Arctic sea ice, could we estimate the correlation coefficient, the R value for this set of data? And we certainly might be able to come up with an estimate for that. So if you think about, fitting a line of best fit to this data, it's pretty darn close, right? Is it perfect? No, but is it pretty strong? Yeah, it's a very strong sort of correlation. So we would expect something like, like a 0.9, but since it's a negative slope, though, it would be more like a negative 0.9. So, if you guess like negative 0.9 or maybe negative 0.85, so somewhere in that range might be kind of a good ballpark estimate for what the correlation coefficient might be for that data.